to get the break in the middle. So in today's lecture, the topics we're going to cover are going to be about the metal forming. So what we learned last week was the casting. We took the metal, we melt it, make it soluble, and we cast it to a different shape. Usually, as we mentioned last week, that the casting is the beginning of any other operation. Raw material for something useful. Sometimes it's a net shape process. That's when we can take the part and use it directly. And that's usually very rare. Usually we need to do an extra process on it to make it useful. Among these processes is the deformation or forming. I can have a steel bar. For example, let's talk about the civil engineering. As it is, it's not going to be useful. I need to make it as a structure. So I need to bend it. That's a forming process. I had the plate, or the castle part is going to be something about 1 meter thickness. I need to roll it, make it thinner, thinner, thinner until I'm going to produce the plate we have in the front of us, something about 3 millimeter thickness sheet. And thus I can do some work on it and make it something useful like what we see here, or the panels for the car. So that's what we're going to go through first, the overview of the metal forming, the metal behavior in the metal forming, the temperature we use in the metal forming, strain rate sensitivity, friction and lubrication in the metal forming. After that, we're going to go in the two branches we have for the metal forming. The first one is the bulk deformation. In the bulk deformation, I'm going to deal with thick parts, bulk parts. Usually going to have a big volume and narrow surface area. And then I'm going to go with the sheet metal working, which is going to deal with the thin parts with wider surface area. So let's start first with the metal forming. So we mentioned that earlier about the stress we have in the metal forming. I can either compress the part, like something similar to what we had in the compression test. And this is including the processes of the rolling, the forging, and the extrusion. I can also add some tensile stresses to stretch the metal. Just simply pull it from both sides like the tensile test to make it thinner, for example. I can add tensile and compress it at the same time to bend the metal. So when you bend a bar, when I bend anything, I can have tensile force on one side and compression on the other side. And also I can use the shear stress to cut the metal. Now when you cut anything actually with the sharp edge, what we're going to have is sliding between the layers of the material. And that's what we call the shear stress. The material properties in the metal forming, usually the material should be having a lower yield strength. If you remember what the yield strength is, the strength value, which is going to be the turning point between the plastic and the elastic zones. We said that the elastic zone, when you are going to have any deformation for the part, is going to retain back to the original position because of the elasticity we have in it. After the yield point is going to have a permanent deformation, or what we call the plastic zone. So usually the material which we are going to be formed must have a lower yield strength. We don't have to add a lot of force to do the work. Also, it must have higher ductility. Higher ductility, that means it does have the ability to be bent without a fracture. And that's, for example, the difference between the wood or the ceramic and the steel. The steel is ductile material, but the problem is it does have a higher yield strength, but does have higher ductility. The metal ductility will simply increase, and the yield strength is going to decrease by increasing the metal temperatures. And that's why usually the forging process is going to be combined with heating the parts. Again, to make it more flexible, and again to reduce the force required to do the work on it. Other factors like the strain rate and diffraction also affecting the metal forming process. Usually I would like to have less diffraction because this will cause a problem during the process of the metal forming. So the types of the metal forming processes can be classified into a bulk deformation process and the sheet metal working. So for the bulk deformation, it's going to be classified into a rolling process. If you ever heard about the name of the steel mill, because actually it does have rollers, put the steel on one side and going to make it thinner until we're going to have a thin sheet on the other side. That's the rolling process. The forging process, you know what the forging is. Extrusion process and the wire bar drawings are actually almost the same process, but in opposite way. So in the extrusion process, something similar to the toothpaste. Toothpaste tube, you're going to have the paste side, you have the die, which is the exit. If I'm going to squeeze it, I'm going to force the material to go through the die, which is going to have a cylindrical shape. Same thing can be done with the metals. I can put the metal on one side, compress it, force it to go through the die, and it's going to have the shape of the die. For the wire and bar drawing, usually this wire you have it in your phone, your computer, and everywhere, something about 0.1 or 0.2 millimeter diameter. Actually, it was 10 millimeter diameter or even 20 millimeter diameter. But we draw it through a multiple dies. Each one is going to make it smaller, and we're going to have the one we use. For the sheet metal working, it can be classified to the bending operations. We can have the deep or the cup drawing, and that's the example we had last week when we made the cylinder for the gas. Towards the disc, we compress it in the with the die and the cylinder, and we have the cylindrical shape, deep drawing process. I can have the shearing process for cutting and other miscellaneous processes we are going to go through by the end of this slide. So for the bulk deformation processes, usually the work part is going to have a relatively low surface to volume ratio. This volume is too big, so when you divide the surface area to it, it's going to have a small ratio. Simple geometries like a cylindrical belts or rectangular bars have a significant deformation and massive shape changes when we are going to add the things, the workforce on it. And that's what we can see in the four processes we had here. That's the rolling. You can see that we have massive change in the thickness, the forging process, the extrusion process, and the bar drawing process. In the sheet metal working, geometry is going to have high surface area to the volume ratio because we are going to have thin but wide area for the part. The process of forming is going to include the bending, the cutting, and extra is called the sheet metal working or the press working because those operations are going to be performed on the press machine. The parts are going to be called the stamping, and the tooling is going to be usually the punch and die. So you can see in all these operations, there's the deep drawing. You can have the punch and die to form the shape required. The material behavior in the metal forming. Usually, the material is going to be in the plastic region of stress strain curve primary interest because the material is going to be plastically deformed. So all the work should be passing the point of the turning point, the one we mentioned earlier, to go from the elastic zone to the plastic zone. So the plastic region of the metal behavior is expressed by the following curve. The sigma is equal to the K multiplied by the mu up to power n. K is the strength of coefficient for different materials, different value for the K, and the n is strain hardening exponent for the material. The flow curve is based on the true stress and strain diagram we covered earlier. So we must pass the yield point to do the work. But the Y bar F is the most important point we have to follow, which is called the flow stress. The flow stress is, for most metal at room temperature, usually strength is going to increase when deformed due to the strain hardening process. So we mentioned that earlier, we talked about strain hardening. Strain hardening, we're changing the dimension of the parts, and thus is going to be stronger. And that's actually what's happened if you try to deform anything. The resistance of the pressure you're going to have, even from this point edge thing, is going to be harder when you press further, right? That's the strain hardening for the material. So once again, the strength is going to increase when it's going to get deformed. The flow stress definition is the threat that must be applied to cause the material to be deformed at a constant strain rate in the plastic range. So I highlight these things in red because, well, you have to remember what the definition of these names. So the flow stress is defined by the equation we mentioned earlier. The YF flow stress is equal to the K multiplied by the mu up to power n. For the K and the mu, we mentioned that earlier in the previous page. Strength coefficient for the material, and the n is strain hardening exponent. And once again, it's different from one material to another. So now, if this flow stress is a stress required to make the material to get deformed, what's your plan as an engineer? You need to save power when you do the work. To save power, we need to reduce this value, right? And that's what we're going to see next, depending on the process we are going to make in the deformation. So the temperature is going to reduce the value for the YF. And that's why in most of the deformation operation, we're heating the part pre-working on it. So as the metal temperature is going to be increased, the K and N value will be decreased. And thus, the flow stress value will be decreased. So the lower forces and the power to accomplish the work is going to be less at the elevated temperature. We have three temperature ranges in the metal forming. We can do the work of what we call the cold working. The cold working is any temperature from the room temperature to a certain amount of the heat, which may go up to 150 degrees. The warm working, which is any temperature less than the half of the melting point temperature, and hot working is going to be the higher temperature. For cold working is usually performed at the room temperature or slightly above. Many cold forming processes are important mass production operation because again, to have the part deformed directly without passing through the heating process, which is going to take a time for that. Those operations usually is going to be a near net shapes or net shape processes, where the minimum machining required after we do the deforming. The warm working is going to start at a temperature which is going to be equal to 0.3, the melting point. So performed at above room temperature, but below the recrystallization temperature. Dividing between the cold working and the warm working often expressed in the term of the melting point. So the 0.3, 1/3 of the melting temperature is the temperature required to do the warm working. The hot working, we're going to work above the recrystallization temperature, and that's equal to half of the melting point temperature. So from 25 degrees up to 0.3 of the melting temperature, that's considered to be a cold working. After that is going to be the warm working. Up to 0.5 is going to be the hot working. Above the 0.5 is going to be the hot working process. So what's happening when I'm going to increase in temperature, the metal will continue to soften over the warm working as the temperature is going to increase above 45 and enhancing the advantage of the hot working above this level. So what are the advantages of each? Now, for the first one is cold metal, and I'm going to form it. I hadn't add any temperature on it, no heat. That means I'm not going to expand it. All the work is going to be more accurate in the dimensions. It's going to cause better surface finishing because actually when you heat the part, you're going to have generated crust on the top. And this will not going to be happening in the cold working. Strain hardening will increase strength and the hardness of the metal. And the grain flow during the deformation can cause a desirable directional properties in the products and no heating of the work is required. That make it a more economical process. And the warm working, lower force because the value of the YF, the flow rate, has been lowered. More interacted work geometries are possible because now I can form it much easier. And usually it's going to need for annealing to be reduced or eliminated because we didn't reach the recrystallization temperature yet. For the hot working, now it's going to be significantly altered because it became too soft. The flow force is going to be much less. Lower forces and power required. The metals are usually going to be fractured in the cold working, can be hot formed. Why? Now, with the metal in the cold working, going to be fractured when you do the formation. It's not going to be happen in the hot working. Why? Because it became more ductile material. It's not a fracture. It's not brittle anymore. And the strength properties of the product generally going to be isotropic, and no strengthening of the part occurs from the work hardening. Now, these are the advantages, but all the three operations have disadvantages. First one is for the cold working, we required higher forces and the power for the deformation because strain hardening is going to make the things worse. Starting work surface must be free of scale and dirt to prevent the fraction. The ductility and the strain hardening limit the amount of deforming that can be done. Otherwise, it's going to get fracture. In the warm working, we need to heat the part. And this will be time consuming and energy consuming. In the hot working, lower dimensional accuracy because your part will be expand and then it's going to be retract once again. Higher total energy required than both the warm working and the cold working. The work surface oxidation will occur, and I'm going to show you a photo for that. Usually when you heat the part to a higher temperature, we're going to have a scale of the oxidation on the part, and by deformation it will be cracked down. This will result in bad surface finishing and losing the dimension accuracy. And usually it's going to have shorter tool life because it's going to be exerted to the heat most of the time. Now for the strain rate sensitivity test. Strain rate is a change in the strain of the material with respect to the time. The strain rate is defined by the equation. Strain rate is equal to the volume divided by the insidious height of the speed of the deformation by the height of the part. Now, just consider that we are working in the compression test. The sample have a certain height. Now, the velocity of compressing this part divided by the instantaneous height of it will give you the strain rate value. Theoretically, for the metal in the hot working, it's behave as perfectly plastic material. Just keep changing without any added extra forces on it. And that means that the value of the N is going to be equal to 0. Thus, the equation of the YF is going to be equal to K only. Just constant force to be added to change the shape. The metal should be continuous flow in the same flow stress once the stress is going to be reached. The flow stress is going to be a function of the temperature in this case. We said that the value of the flow rate is going to go lower as the temperature is going to be increased. At hot working temperature, the flow stress depends on the strain rate value. As the strain rate is going to increase, the resistance to deformation will increase, and this is the effect known as the strain rate sensitivity. Now, that's usually happen. Now, as I told you earlier, when you compress anything, it's going to resist the compression on it as long as you're going to compress it further. So that's what's happening in the effect of the strain rate, the flow stress at elevated work temperature. Is going to be a curve shape, and that's relationship, the same relationship employed in the log-log shape. So the effect on temperature of flow stress, as we mentioned earlier, we are going to combine the strain rate sensitivity with the equation of the flow stress. So the flow stress in this case is going to be equal to the strength constant multiplied by the strain rate up to power m, which is the slope of the log-to-log flow stress with the strain rate value. Okay. Now, some observation about the strain rate sensitivity. Once again, we said an increasing the temperature will decrease the value of the C and increase the N value. At room temperature, the effect of the strain rate almost negligible, and the flow curve alone is going to be a good representation for the metal behavior. As temperature is going to increase, strain rate will become increasingly important in the determining of the flow stress value. Now, usually diffraction is going to cause a problem in the metal forming process because it's going to be adding an extra force resistance to the process itself. And that's what we're going to see, especially in the forging and the extrusion process. It does have an effect on the rolling process, but it's not going to be at the same rate. So in the most metal forming processes, diffraction is going to be undesirable, as any other operation we are going to have. So metal flow is going to be reduced due to the resistance of the friction. The force and the power is going to increase, and the tool wear will be faster. Friction and the tool wear are more severe in the hot working process, and thus we're using the lubrication in the metal forming. So the lubrication mainly is going to reduce the harmful effect of the friction in the deformation process. The benefit is we're going to reduce the sticking, the forces, the power, and the tool wear. And we're going to have better surface finishing because of these reductions. And it's going to remove the heat from the tooling, thus we're going to have longer life for the tools. So we are going to go through the main bulk deformation process in the metal forming, which are the rolling and other operations related to the rolling, the forging, the other deformation related to the forging, extrusion, and wire and bar drawing operations. So once again, we said that the bulk deformation is mainly going to be done on a bulk material. Volume is going to be big, so volume to the area to volume ratio is going to be usually small. The forming operation will cause a significant change shape. It can be block, and again change it to a cylindrical shape in some processes. A block and make it as a sheet. So this can be done by the forming of the sheet deformation with the initial form is going to be bulk rather than a sheet shape. The starting forms can be cylindrical bars and pellets, rectangular pellets, slabs, and similar shapes. And this process stresses the metal significantly to cause the plastic flow into desired shape, and usually performed as a cold, warm, or hot working. So in hot working, significant shape change can be accomplished. Now we know why, because the flow stress is going to be reduced. Ductility of the material is going to be increased, right? That's the main thing. In the cold working, the strength is going to increase during the shape changes because we are going to have the strain strength. Little or no waste in the bulk deformation process. Some operations are going to be near net shape or net shape processes. And the part will require simply a little or no subsequent machining after the deformation process. So the four basic deformation processes, the rolling, where we are going to have a slab or a plate is going to be squeezed between the opposite rolls. The forging, the work is going to be squeezed and shaped between opposing dies. The extrusion, the work is going to be squeezed through the die opening, thereby is going to take in the shape of the opening. And last one is the wire and the bar drawing, where the diameter of the wire or the bar is going to be reduced by pulling through the die openings with S, by the way, multiple openings until we're going to make it smaller. So that's the rolling. Two rollers going to rotate in opposite direction. We're going to have friction at this point, and this friction will pull the bulk inside between two rollers. The pressure between the rollers will do the deformation process. So the part is going to get thinner. Now, because the part is going to get thinner, we must know that the volume of the part is constant. So what's happening if it's going to be constant volume, but now the section is get thinner? So what's happened? something decreased, so something else should be increasing. Yeah, the width and the length. Yeah, the width and length is going to increase, thus the volume is going to be constant. So to achieve the deformation in the rolling process, the work thickness is going to be reduced by a compressive forces exerted by the two opposite rolling, as you can see. So the rolls are going to do two things. First, due to the friction at the entrance, we are going to have a friction. And this friction will pull the work into the gap between them. At the same time, because the distance between them is constant, this will be simply squeeze the work to reduce its cross section. So these are some shapes can be done with the rolling operation. If I'm going to have the bloom, I can simply make the structural shapes like the I-beam and the rail shape. Now, these usually are going to be a net shape parts. You don't have to do any extra machining on it to use it. Maybe the drilling of the holes to fix it in the structure. Also, I can use the slab, make it thinner to make a plate sheets or the coils. I can get the pellet and change it into the bars or rod. The types of the rolling we have usually is going to be classified based on the working geometry or based on the work temperature. Based on the work geometry, this can be flat rolling. We're just going to reduce the thickness without changing the shape. Can be a shape rolling, where the square cross section is going to be formed in a shape such as the beam, like what we saw in the previous one. So if you take back a look on the previous one, this is the shaping, and this is the flat rolling. Okay, the shape rolling and the flat rolling. Now, also can be classified depending on the work temperature. I can increase the temperature to make the things easier because the flow stress is going to be less, and that's what we call the hot rolling. And I can do the cold rolling, which can be done in the room temperature to reduce the sheet and the plate stock. The flat rolling, two rollers, well, I think you have an example for that, right? So this is side view. These are the two rollers. I'm pulling the part. It does have initial height, and it's going to end up with the new height, which is going to be equal to the gap between the two rollers. The difference between the original thickness and the final thickness we call the draft. The reduction value is the draft divided by the original thickness. And that's what we call the reduction value, R. The other process is called the shape rolling. Now, in this case, the rollers are not going to be pure cylindrical shape. It's going to have a negative shape of the parts I would like to form. And the shape rolls are used to produce the construction shapes such as the I-beam, the L-beam, and the U-channels. The rails are for the railroad tracks and round and square bars and roads. Usually, it's going to be deformed in the counter cross section rather than the flat shape, and accomplished by passing the work through a rollers which is going to have a reverse of the desired shape of my work. The rolling mills, which is going to be consist of a series of pairs of rollers. So the equipment usually is going to be massive and expensive. The rolling mill configuration can be the two heights, which is the normal one. I can have the three heights, so each one is going to take it to a new thickness. I can have the cluster type, the four heights. Now, this usually is going to be used to reduce the power required to turn the things. I can have the cluster mill, and I can have the tandem rolling mill. Now, once again, each one is going to take it to a new thickness. If you are going to have the chance to visit the Blue Scope in Wollongong, that's what you are going to see. So the melting of the material is happening on one side. Then we're going to roll it over the rollers and then force it to go between the two rollers in the rolling process to form the shape at the desired thickness. Other deformations which are related to the rolling are the thread rolling, the ring roller, the gear rollings, and the roll piercing. So actually, all the screws and thread you're using in your daily life were not machined on the turning machine one by one. It's very simple. We have the bar, the rod, and we run it between two rollers which have the thread shape, and thus the thread is going to be printed on the part. That's what we call the thread rolling. In certain application, we're going to have a small ring and we want to expand it and minimize the height. That's what we call the ring rollers. And the gear rollings and the roll pressing is going to go next. So this is the thread rolling. The raw material is going to be just a bar. We run it between two rollers which have the thread shape, and this will form the threads on the screw or the bolt. So it's metal rolling process used extensively in the manufacturing industry to produce mass production of the screws. Important for the mass production of the bolts and screw because you don't spend time on the machining. It's all going to be done in the matter of seconds. Performed as a cold work in the thread rolling machine. The advantage is higher production rate, better material utilization because there will be no lost material, stronger thread, and better fatigue resistance for the part. Now, this is the ring rolling, the formation process in which the thick-walled ring is going to be expanded to have a smaller diameter, from a small diameter into a thin-walled ring of larger diameter. Thick-walled ring is going to be compressed at the same time it's going to be elongated, causing the diameter to enlarge. Usually it's going to be done in hot working process, but sometimes it can be done in cold working for the smaller rings. So that's what's happened. This is the original shape. Now we can see that he's doing actually continuous cooling for the mold. Okay, so we press it and expand it at the same time. We make it thinner, bigger diameter. Now the main process for this one is to make the rings for the ball bearings, the big one. The roller pressing is simply making a hole by using the mandrel. So the rollers will force the part, which is rotating at the same time, to be penetrated by the mandrel, and we're going to have the hole inside. Now the other operation is the forging. Third operation is the forging process. Now, the forging process is one of the eldest methods done after the process of the casting. It's deformation in which the work is going to be compressed between two dies. What was the die in the old days? Hammer is the upper, okay, and the saddle is the second. The products can be the engine crankshaft, the connecting rods, the gears, the jet engine, and the turbine parts. Also, some basic industries use the forging to establish shape of the large parts and machine it to final geometry and size. You can have it as a cold or hot forging. Hot or warm forging, the advantage is going to be the reduction of the strength and the increased ductility of the work metal, as we mentioned earlier. Cold forging, the advantage is the increased strength due to the strength hardening. And we gave an example for both. Strength hardening, we talked about the shell done in the movie when he's tried to forging the things, make it thinner, but it was strain hardened. Okay, for the impact with press forging. Some of the forging simply by adding the force continuously, and that's what we call the press forging. Or we can use the hammer, and this will be the impact one. Now, it's very rare to use the manual hammer in the forging. They're using the hydraulic hammer to do that. Do the same work exactly. So the types of the forging operation can be the open die forging. Just two dies, that's the classical method to form the shape. We can have the impression die forging process. And in this operation, we are going to have something called the flash from this side. You can see when it's going to reach this stage, the excessive material will leave from this side. We can have a flashless forging where no excessive flash is going to be created, but usually the shape is going to be less complicated in geometry. So once again, type of the forging operation, the open type, the impression die forging, and that's what the flash we talked about. And we have the flash stretch forging process. Now, this flash actually is going to be waste material. We have to trim it later. But it does play a very good role because it's going to provide an escape for the material. Thus, the material is going to fill the whole cavity of the dies. And thus, we're going to have a full shape for it. This process, because it's going to have the punch and the die closed area, and we have to compress it, is going to be an edge-shaped part, yes. But the problem is that if I go to compress something inside the die, I need to take it out. So usually the shape is going to be less complicated and must be symmetrical shape. So that's what's happening in the open die forging. Now this is the crust I told you about. This is oxidized material to the high temperature. When you're going to press it, it's going to fall down, and this will change the volume of the metal I have by a certain amount. And of course, the resultant is going to be a bad surface finishing from the side. Now we can see that it's not going to be a pure cylindrical shape. We have something like the barrel shape. And this process is called the barreling. And this mainly happened due to the friction between the die and the work part area. So it's not going to allow it to go freely. It's going to hold at the top, and that's what's called the barreling process. So open die forging, compression of the work part between the two flat dies similar to the compression test. The formation operation will reduce the height and increase the diameter of the work part. The volume must be constant. Common names including the upsetting or the upset forging. So this is the ideal case. No barreling. We consider there's no friction, and thus the strain in this case is going to be equal to the natural logarithm of the original height divided by the final height. This happening with no friction, which is, as I told you, is an ideal case. It's impossible to happen. If no friction occurs between the work and the die surface, we're going to have homogeneous deformation occurs. The true strain can be calculated directly from this equation. The open die with the friction, we're going to have the barreling to occur. That's real life. So in this case, the effect is going to be even more pronounced due to the heat transfer at the die surfaces, which cools the metal and increases its resistance to deformation. The impression die forging now is not going to be a flat die. In this case, it's going to have a negative shape of the part I would like to make. I can show you next video as well. The compression of the flow of the work part dies with the inverse desired part shape. In this case, we are going to have the flash to occur by the metal that flow beyond the die cavity into a small gap between the die plates. Actually, they were designed to stop at a certain height to allow for the flash to present. So the flash must be later to be trimmed, but it served an important function during the compression. Now, for this part, try to remember what the use of the flash we have in the case of the impression die forging. As a flash form, the friction resist continues the metal flow into the gap, constructing the metal to fill the die cavity. In the hot forging, the metal flow is going to be further restricted by the cooling against the die plate. So these are one of the examples. As you can see that the stress is going to increase as we deform it further because of the strain strength we're going to have. Okay, until we stop, this is the flash has been generated. So the advantage of the impression die forging are the higher production rate, less waste of the metal, generate greater strength for the material, and favorable grain orientation in the metal. The limitation is not capable of the close tolerances because we still have to remove something. And the machining often is going to be required to achieve the accuracies and the features needed. Most of the spanners are actually done by this process. The spanner we use are actually made by the impression die forging. So the other process is the flashless forging, which is going to be done in a closed die process. No flash will be generated. Almost the geometry diameter will be as the desired one. Okay, So starting work volume is going to be equal to the die cavity volume within the very close tolerances. The process control more demanding than the impressive die forging, best suited for the part geometries that are going to be simple and symmetrical so we can take it out from the mold. Often classified as the precision forging process because I know what the volume of the final part. So I can add the material which have the same volume. When I'm going to compress, I'm going to have exactly the same dimensions. Now, these are the forging hammers. So once again, this is a hydraulic forging hammer doing this exactly the same thing like what the old people used to do. Apply the impact load against the work part in two types. Either gravity drop hammers, we take it up, then we release it, and then it's going to have the acceleration to get the impact, or can do it by the power drop hammers, which accelerate the arm by the pressurized air or the steam at the top. Disadvantage is usually the impact energy transmitted through the anvil into the floor of the building, so the building just keeps shaking all the time. Commonly used for the impression die forging process. So these are some of the forging presses process we have, which apply the gradual pressure to accomplish the compression operation instead of the impacting. The types can be the mechanical press, which convert the rotation of the driver motor into a linear motion of the ram. I can use the hydraulic press. I can use the screw press, like the one we use in the old printers. The other process we have, which related to the forging, is the upsetting and the heading. Now, once again, we go back to the screw and the nuts. To make the head of it, we're going to use the upsetting and the heading process. Forging process used to form the heads on the nail, bolts, and similar hardware products. More parts produced by the upsetting than any other forging operations can be performed as cold, warm, or hot on a machine which called the header or the former. The wire or bar stocks is going to be fed into the machine and head, then the piece is going to be cut to length, and for both and the screw, the thread rolling is going to be then used to form the threads on it. So that's the process. We cut it to a length, then we're going to put it in die to make the head shape. That's the upset forging, and this is the heading, which is the upset forging process as well. So this is the type where we're going to have the wire stocks going to be fed and stopped. Then we're going to compress it inside the die, and we're going to have the shape generated. The other one is the heading, which is going to be the process of we taking the wire up, we compress it to a different shape inside the die. The other process is called the swagging. Now in the swagging, we're going to have at least 4 parts die. It's going to keep opening and close as the part moving within. And this is a very simple operation because what we're going to have inside is going to be copied on the mandrel shape. So the shape metal using this swatch, and especially in order to use the cross section, accomplished by rotating dies that are going to have a hammer process on the workpiece, radially and vertically taper it as the piece is going to be fed into the die. Used to reduce the diameter of the tube or the solid rod stock, and mandrel is going to be sometimes required to control the shape and the size of the internal diameter of the tabular parts. The swagging of and the radial forging process. Now, in this case, as we mentioned, that the die is going to be rotating. The part is, is going to be swagging, and the part is going to be rotating. And this is for the solid part. We're going to reduce the diameter to a new shape with the present of the taper. Swagging process is used to reduce the solid rod stock, where the dies rotate as they're going to be hammer on the work, and thus is going to make it smaller with the same amount with all the dimensions. In the radial forging, the workpiece is going to rotate while the dies remain fixed orientation and are going to be hammering the work. The trimming process is also considered as a forging process. Now, for example, when we're going to have the flash occurred from the previous operation. To do that, simply I'm going to have the die and the RAM and produce the process of the trimming. Trimming is cutting operation performed on the formed part to remove the excessive metals and establish a new size. Usually done while the work is still hot, so the separate trimming process is going to be included in the forging station. Now the other operation is the extrusion, and I tell you that the simplest example for that is going to be the toothpaste process, or even the cream applicator in the cake process. Different dies is going to give you different shapes, but in this case we're going to put the metal inside. So extrusion is a compression forming process in which the work metal is going to be forced to flow through a die opening to produce the desired shape. We mentioned that. In general, the extrusion is going to be used to produce a long parts of the uniform cross section. That's the only process we can do. We're just running through the die. We're always going to have the same shape, but it's going to be a long parts usually. Have two basic, either going to be a direct extrusion or the indirect extrusion. Now, this is direct extrusion. That's the container. This is the die. I'm going to use the ram to push the metal to go through the die and have the final work shape. So it's direct. Just push it and force it to go through the die. Also called the forward extrusion. Starting pellet cross section usually going to be round. The final cross section of the shape extruded determined by the die opening shape. As the ram is going to approach the die opening, a small portion of the pellet will remain at the end. As you can see here, this is a table shape. So we're going to have some material left here, and that's what's called the butt. Usually the butt needs to be removed because this butt needs to be removed from the work, and because it's not part of the work at the end. Now in this case, this is the hollow and semi-hollow shapes which can be done using the extrusion process. Simply we're going to add the mandrel in the middle of the die, of the ram. And first one, we're going to force the material. We're going to have a hollow shape in the middle. I can change it to a different shape to have a different hollow parameters in the middle. This is an example for the work. Now the indirect extrusion, in this case, the die is going to be a part of the ram, like that. So as I'm going to push the material, I'm going to force it to come my way. So that's what we call the backward extrusion. Now the only advantage of this is we're not going to have a loss of the material, which is the butt. But in all the cases, we are going to have a shorter part because it should be limited to be less than the length of the ram itself. So limitation of the indirect extrusion are going to be imposed by the low rigidity of the hull ram and difficulty supporting the extruded parts as is going to exit from the die. The advantage of the extrusion are we can have a variety of the shape possible, especially in the hot extrusion process. But the limitation is that the part cross section must be uniform through the length. The grain structure and the strength enhanced in the cold and warm extrusion. Close tolerances are possible, especially in the cold extrusion, and in some operation, little or no waste material can be achieved. The comparison between the hot and the cold extrusion are in the hot extrusion, prior heating of the pellets are going to be required, and it's usually going to be above the recrystallization temperature. So anyone here remember what the recrystallization temperature is? What was the recrystallization temperature? Half of the melting point, okay? Half of the melting temperature. So by increasing the temperature, as we mentioned once again, we're going to reduce the strength and increase the ductility of the metal, permitting for more size reduction and more complex shape to be achieved. And the cold extrusion generally used to produce the discrete parts, which is a smaller one, because we cannot make it a long, it's cold. Okay, and thus the impact extrusion is going to be used to indicate the high-speed cold extrusion process. Now, in opposite to the extrusion, where I force the material by pressure to go through the die, I can have the other process which is widely used to make the wires and the bars, which is called the wire and bar drawing. Now, this one is not extrusion. This one is a drawing from the other side. So the cross section of the bar, the rod, the wire is going to be reduced by pulling it through the die opening. Similar to the extrusion, except that the work is going to be pulled through the die drawing and is pushed through the extrusion process. Although the drawing applies the tensile stress, the compression also plays a significant role since the metal is going to be squeezed as it's going to be passed through the die opening. So the reduction in the area we have through the bar process is bar drawing process is going to be equal to the original area minus the final area divided by the original area. This will give you a percentage of the reduction we have in the area. Usually it's not going to be one die. Usually it's going to be a multiple dies. Each one is going to be reduced by a certain amount to get the final diameter for the part. So the practice and the products for the drawings are, the drawing practice, we can usually use it as a cold work. And usually, most frequently used for the round cross section, but can be used for the rectangular and the square shape. The products are going to be the wires, the rod stock for the nails, the bar stocks for the other material, for example, for the machining, the forging, and the other processes. So in the wire drawing, we're going to pass it through multiple dies until we're going to achieve the final diameter for the wire. Now, because we cannot just simply withdraw it for a long distance, we're going to use rollers, which called the capstan drums. So if I'm going to show you a video, I'll try to show you a video for that, or the actual wire drawing machine. I will take the shortest one. So you can see that the diameter is simply reducing each time we pass it through one of the dies. So now what's the use of these rollers, the capstan drum? What will be the use of that? Now I showed that actually the diameter was big and it was revolving around in multiple times. So this will going to use less force to pull the part through the die. So the difference between the wire drawing with the bar drawing. Difference are going to be mainly in the stock size. The bar always going to be big size, and we're going to make it to a quite big size. But in the case of the wire, it's going to be too small. So the bar drawing, large diameter bars and the rod stock is going to be resulted. And the wire drawing, small diameter stocks, the wire size can go down to 0.03 millimeters, like the one we're using, as I mentioned once again, in the most of the electronic devices. So the machine mechanics are the same, but the methods and the equipment are going to be even quietly different. So this is bar drawing. Again, to need more force to do that. It's not going to be able to be run around the drum. Accomplished by a single draft operation, the stock is going to be pulled through the one die opening to reduce the dimensions. The beginning stock has a large diameter and straight cylinder, and requires a patch type operation. That's means we're not going to make it in very long distance. It always should be short one. Now, away from the bulk deformation, we're going to talk about the sheet metal working operations. Now we're going with the thin sheets. We're going to have a high ratio for the area over the volume, which are the cutting operation first, the bending operation, the drawing again, the other sheet metal forming operations, the dies and the presses for sheet metal processes, the sheet metal operation not performed on the press machine, and the bending of the tube stock is going to be covered here. So for the sheet metal working to be defined, is cutting and forming an operation performed on a relatively thin sheet of the metal. When we say a sheet of the metal, the sheet that means that the thickness is going to be equal to 0.4 millimeters up to 6 millimeters. Anything in between these values, we call it a sheet. So now, what do we have here is a sheet, less than 6 millimeters. This one is a 4. Okay, if the thickness is going to be more than 6 millimeters, we're going to call the plate. The other thing is that you can say that the plate can hold itself, is going to be suspended. The sheet cannot. That's the general talk. Usually are going to be performed in cold working. You don't have to heat it up, usually. The sheet and the plate metal parts for consumer and industrial products such as the automobile and the trucks panels, the airplanes panels, and railways and car locomotive panels. The advantage of the sheet metal parts are going to have high strength, good dimensional accuracy, good surface finishing, relatively low cost, and economical mass production for large quantities. The metal working terminology for the sheet metal working, we can use the punch and die tooling. Okay, now one of the process, for example, I can put it on the side. This is my die, the punch and cut it, or shape it, or whatever the thing is. I can use this process, which is a machine tool that performs most of the sheet metal operations, and I can do the stamping process for the sheet metal products. Basic types of the sheet metal process are the cutting, which can be done by the shearing, the blanking, or the punching. I can do the bending process on it, and I can do the drawing process on it, like the shape of the cylindrical cylinder we did last time. Okay, forming the sheet into convex or concave shapes. So this is the sheet metal cutting. So I'm going to have the die and the punch. I should have a clearance between them. Put the press on that. In this area, we're going to have a shear force. The material is going to slide internally. And thus is going to be a fracture at a certain point. Fracture due to the high intensive shear force. That's why we call it the sheet metal cutting with the shear cutting. The shearing, blanking, and the punching cutting, three principal operations using almost the same process, like that sheet metal cutting process with the shear cutting. The shearing, the blanking, and the punching. Have you seen this machine? We have one, right? At the corner. So it's actually performing the shearing operation. Now, can you tell me why the plate is inclined? Why the plate is inclined, not straight? Sorry? No, not that. Increase the pressure because less contact area here. So we're going to have less force exerted, higher pressure on the work part, thus the cut is going to be faster. So the shearing punch is going to apply at a certain velocity, start the contact at one point, exert the highest pressure on the point, so the shearing will start at one end, then continue to the other end. Now we have two operations. We have the blanking and we have the punching. And the blanking, the cutted part is going to be used for another operation. So we made a blank for the operation. But in the case of the plate in the front of you in the disc, it does have holes. So the small stock I took off it from the material actually is going to be a scrap. And in this case, we call it the slug or the scrap, and the operation is called the punching. The punching is the process of making the holes, but not taking the parts to use it for another operation. Okay. So this is a blanking operation because this is not the use part. The one I produce is going to be used for the further operation. And this is the punching operation, making a multiple hole, like the background of the, not this one, the desktop computer tower. The clearance in the sheet metal is very important. I should have a clearance to prevent the excessive forces due to diffraction. I think I put this part because there was a question about the clearance we have in the sheet metal cutting. So distance between the punch cutting edge and the die cutting edge are very important. Usually the value is going to be in the range of 4% or and 8% of the stock thickness. If too small, the fractal lines pass each other, causing the double burnishing and the larger forces. If too large, the metal is going to be pinched between the cutting edge and the excessive burr will result. We also can have the angular clearance, which allows the slug of the blank to drop through the die without stocking in the middle. And typical value is going to be something between the 1/4 to 1.5 degree on each side. The punch and the die size for the round blank, that's a blank. The diameter have dB. The blank and punch diameter is going to be equal to the blank diameter minus 2 multiplied by the clearance. The blank and die diameter is dB, and the C is the clearance we should have. For the round hole, now I'm doing the punching, not the blanking. The hole punch diameter is equal to DH. The hole diameter is going to be DH plus 2 clearance. So that's the shape we're talking about. There's the punch size. This is the punch diameter. This is the clearance. So the diameter in the case of the blanking is going to be equal to the blanking I would like to make, the blanking diameter, okay, minus 2C. In the case of the round hole, and now I'm making a hole, so the hole punch diameter is going to be, sorry, the hole die diameter is going to be equal to the DH value plus the clearance times 2. The force cutting is very important to have this force cutting, and this will be in tonnage. Is going to be the STL. The S is shear strength of the metal, T is the stock thickness, and the L is the length of the cutting edge. The sheet metal bending is simply by adding the force in one direction to cause the, like this case, that's the bending from the sides. Okay, so what's happened when I'm going to add the bending on the sheet, we're going to have both the tension and the compression on the part. So the metal is going to be compressed from inside, getting stronger, while it's getting weaker from the outside because it's going to get stretched. Tension and compression from the middle. And inside, we're going to have the neutral axis, where the value of the stress is going to be equal to 0. The straining of the sheet metal around this strain axis to take the permanent bend. The metal inside the neutral axis is going to be compressed, and the outsides of the neutral axis is going to be stretched. The V bending is one type of the sheet metal bending performed with the V-shaped die. So we're going to have the die have V shape, and the punch is going to have V shape. Adding the force, we're going to have the V-shaped cutting. Usually performed on the V-shaped die with low protection, performed on the pressure brake, and the V-dies are going to be simple and inexpensive. And also I can use the edge bending, and I think we still have this machine downstairs. So just making the bending by using the complicated machine. Now in this case we are going to have 3 parts for the machine, as you can see here, 1, 2, and 3. Or the press pad, which holding the thing, and we have the punch, okay, and thus we are going to have the clearance in between, which is going to be equal to the thickness of the part. The wiping die will have high protection over the V shape, pressure pads are going to be required, the dies are going to be more complicated and of course more costly than the V-shaped type. The stretching during the bending process, if the bender is going to be small relative to the stock thickness, the metal tends to stretch during the bending operation. And accordingly, we have to estimate what will be the stretching value because otherwise we're going to have a crack at the outside. The problem is to remind the length of the neutral axis of the part before the bending is going to be too complicated a process. The bend allowance formula is this one. The bend allowance is equal to 2 pi multiplied by the bend angle divided by 360 multiplied by the bend radius plus the factor of stretching multiplied by the thickness of the stock. One of the operation will happen during the bending is what we're going to see here. So we have some of the energy, kinetic energy, will be stored in the material, which causes the spring back effect. So we thought that we bending the things, that's okay. As we release the force, it's going to be springing back. So an increase in an included angle of the bent part relative to the included angle forming tool after the tool is going to be removed. And the reason for the spring back is going to be the elastic energy remained in the bent part. Spring back is a result and decrease in the bend angle and increase in the bend radius. And that's what's happening during the operation of the bending. The bend force calculation can be done from this equation. The force of the bending is equal to the value of the kPf value, the factor of the bending, multiplied by the T, which is the TS, sorry, the tensile strength of the sheet metal, multiplied by the width of the part, multiplied by the thickness squared divided by the D. So I'm going to leave this one. It's not important. Now the drawing operation, that's the DB drawing operation we talked about earlier, is going to change the sheet shape into a cup shape, for example. Sheet metal forming to make a cup shape, box shaped, and other complex curved hollow shaped parts. The sheet metal blank is going to be positioned over the die cavity, and there is going to be pushed metal into the opening. And the product is going to be the beverage cans, the ammunition shells, automobile body panels, and extra. Also, it's called the DB drawing operation to simply distinguish it from the wired or the bar drawing operation. And that's actually what we saw last time with the making of the cylinder for the gas bottle. Okay, so we hold in part, we send in the punch, and this will cause the part to take the cylindrical shape. The clearance in the drawing usually is going to be equal to 1.1 multiplied by the thickness of the stock we are using. The test of the drawing feasibility is, first we need to check what the drawing ratio, what the reduction value, and what the thickness to diameter ratio. The drawing ratio, dr, is equal to the dB, which is the blank diameter, divided by the punch diameter. This value should be always less or equal to 2. The reduction value, now once again, is the ratio between the part diameter minus the punch diameter divided by the punch diameter. And the value of the R should be less than 0.5. And the last thing is thickness diameter value, or the T divided by the dB. And this should be always greater than 1%. If these three conditions are going to be available, then we can say that this part can be simply DB drawn. This one is not important. Okay, so these are some of the shapes other than the signal shape can be done by the drawing operation. You can have the box shape, square one, the stripped cups, the cones, the cups with the spherical rather than the flat, irregular curved forms, and actually, as I told you earlier, that the car panels are made with the same operation. Now, other sheet metal forming processes can be done on the press machine. We can classify into operation formed with the metal tooling, and we can do it with the flexible rubber tooling. So the ironing is the extension of the length of the drawn cup. Okay, so we take it by a drone, for example, to the thickness of, let's say, 5 millimeter and the length of 50 centimeters. But I would like to take it to 1 meter with 2 or 3 millimeter sides. So I will do the ironing process. The imposing process, like this one, okay, creates the indentations in the sheets, such as the raise, lettering, or the strengthening reps. The goring process, which low tooling course, is going to be a rubber pad, and this is the foam block. This is the metal. I'm going to add the pressure on it. The rubber pad simply is going to get stronger because it's going to get compressed, and this will force the metal to take the shape of the foam block. Other operation not performed on the presses, but they are considered to be a sheet metal working. Stretch forming, the roll bending and the forming, the spinning operation, and high energy rate forming processes. So for the stretch forming, I'm going to extend the length and I'm going to make it thinner. So simply I'm going to force the die to go through constant from both sides, and this will stretch it on the sides. And this is stretched, and similarly is going to be bent to achieve the shape change. And that's usually used to make the satellite receiver dish with this operation. The roll bending, where large metal sheets are going to be, and the plates are going to be formed into a curved sections using the rolls. So I have it as a plate or the sheet, and I would like to make it as a roll. Why I have to do it like that? Why I have to make it as a roll shape? For example, what? No, because I can roll it actually over the thing is going to be doing. But why we have to do a process like that? What do you think that the end will be? The metal barrels, right? I have to roll the sheet, then again to seam seal it from the ends by welding. The other option is the roll forming. Okay, simply again to run the parts through the rollers and to form it to a new shape. And that's, for example, what we have in the case of the highway fence, okay, done by this operation. Now, the spinning operation, most of the aluminum cooking ware done by this operation. And also the small size of the satellite dish receiver is done by this operation. It's a plate, again, to fix it on the rotating machine. And we're going to use the mandrel to form the shape. So simply we're going to force it to take the shape of the mandrel by adding the force on it. It's have three types: conventional spinning, the shear spinning, and the tube spinning. Okay, and the DB drawing. So they just made the cup shape using the DB drawing operation. Okay, now other processes will be done, but by not using a rotating part like what we had earlier, not moving part like what we had earlier. Simply is going to use another energy form, which is going to be high energy rate to form the shape. And this can be simply the explosive forming, the electrohydraulic forming, and the electromagnetic forming process. So in the explosive forming, that's the sheet I would like to form. I would like it to have the shape of this die. So I put it in the water or any other liquid, put an explosive charge that's going to make the waves, which is going to have an impact on the part and push it, to force it to take the shape of the die. But it's conditioned to have a negative pressure inside the die, and this can be done by the vacuum pressure. The other operation is the electromagnetic forming. The coil will going to generate electromagnetic force, and thus the part will be forced to get outside and thus take the shape of the die, that the color forming here. And the last process is the bending of the tube stock. Now, then bending of the stock is going to be done by running through a rollers. That I don't want to damage the radius inside the tube. So this can be done by the stretch bending process of the tube. I can do it with the draw bending of the tube. Now, once again, this approach can be done without having the minimizing of the diameter, internal diameter of the tube process. Okay, so that's it for today. Would you like to see many other operations like the one we had earlier? Or that's it? I can show you some videos for the bending of the tube stock. So you can see here that we have the three parts which doing the process of the bending. No change in the diameter of the bar is going to be happen during the process. So what are they doing with this part? What the use of similar parts? The exhaust tube from the engine usually is going to have bending to achieve the heat reduction. What else do we have here? The explosion forming. I hope they had a video for that. I need a short one. Yeah. So actually this one is going to be a dry type. It doesn't have any fluid inside. Okay. Now, later when we're going to talk about the welding, we can do also welding using the explosion, and that's what we can see in this video.
The strength measured in millions of pounds per square inch. Explosion.
So actually, these are two layers, two metal spots, which has been welded by the explosion. And this is not very rare process. Actually, is done commonly in many of the manufacturers.
Other welding methods. Join nearly every kind of metal combination, no matter the type or composition. To create an explosion, two large pieces of metal are stacked on top of it, then covered with a high-powered explosive. When detonated, the downward force of the explosion welds the two pieces together through a combination of intense force and remarkable physics. The explosion welding process begins as soon as two metal plates arrive at EMC's production facilities. To maximize the welding force of the explosion, the surfaces of each plate are ground as uniformly flat as possible, a process that also removes any rust, oxides, and other surface flaws. They are then ready to be assembled into a pack, which locks the plates into position for the explosion. To build a pack, the stronger and thicker of the two plates is laid face up. From now on, this plate will be identified as the back. Small metal spacers of equal height are then packed onto the surface of the backer in a uniform grid. These spacers will maintain a set gap between the backer and the second plate, which is placed on top. This second plate is thinner than the backer and is called the cladder. The standoff gap between the backer and cladder is less than an inch in height, yet without it, the explosion weld would be impossible. EMC uses an explosive powder that is a proprietary blend of common and unique explosive chemicals. The amount and exact formulation is always matched to the types of metals involved. Once the pack is set, the explosion is initiated at one end of the pack and moves across the upper level of the pack at a uniform speed. This explosive front progressively guides the cladder plate downward toward the back at the slight collision angle caused by the standoff gap. Forward of the collision point, air is forced at high velocity. All oxides and impurities are expelled, rendering the plate surfaces metallurgically pure and ideal for a weld. As the backer and cladder collide, the weld is created nearly instantaneously across the entire surface of the plate. Not surprisingly.
Okay, so we'll cover this one later. I think that's it for today. Thank you for your attendance.